All right, welcome to this explainer. Today, we are diving deep into the realities of backend architecture, data lakes, and distributed systems. We're going to strip away all the illusions of seniority and look at the brutal, messy truth of scaling and actually surviving production systems. Look, if you think the gap between a mid-level dev and a senior architect is just the ability to write mind-bending code, well, you're in for a massive wake-up call. We're going to look at the hard data, the postmortems, and those dreaded 3 a.m. pager alerts to show you exactly why.
So let's just dive right in and shatter absolutely the biggest myth in our entire industry. There is this incredibly pervasive idea that senior developers are just sitting there typing out mathematically perfect algorithms all day long. We picture them architecting these beautiful, pristine microservices from scratch. But, the actual data from thousands of enterprise commits reveals a completely different reality. Fundamentally, senior developers don't write better code.
Which, naturally, leads us to a pretty glaring question. If their immense value isn't about writing the most elegant logic or, mastering the flashiest new frameworks, what exactly are they doing all day? How do they get promoted and justify those massive salaries?
The answer is shockingly simple, but it's totally counterintuitive. They become ruthless deleters of code. They manage technical debt and cognitive load by deleting systems that honestly never should have existed in the first place. You see, every single line of code is a liability. It's something that has to be maintained, tested, and understood by the next poor soul who inherits it. Senior engineers know that the absolute most effective way to optimize a system is to literally remove the moving parts.
To put that into perspective, a junior developer might impress management their first year by adding, say, 50,000 lines of code. They're building massive abstractions, creating mountain peaks on their GitHub contribution graph. But a senior engineer, they'll join that same team and immediately delete 15,000 lines. They strip out unused features, they kill premature optimizations, and they consolidate bloated utilities. They inherently understand that reducing cognitive load is exponentially more valuable than just blindly adding new functionality.
All right, moving on to Section 2, Database and Latency Traps.
Writing less code is really just the start. You also have to stop writing terrible database queries. And the undisputed king of application-level latency is the N+1 query problem. It happens all the time. You think you're keeping your ORM logic super clean and abstracted. You fetch a list of authors, and then as you loop through them, you fetch their books. Seems harmless, right? But behind the scenes, that N+1 approach turns a single, simple operation into an absolute latency nightmare, hammering your database with hundreds of sequential network calls.
And the penalty for this is catastrophic. By simply replacing that lazy N+1 loop with an optimized eager loading approach, like using a join or an in-clause batch, you can achieve a massive 54x performance improvement. And real-world benchmarks, we're talking about dropping response times from a sluggish 808 milliseconds down to a lightning-fast 15 milliseconds. It's a total game changer.
But hey, fixing your queries isn't going to save you if your foundation is literally rotting. Blindly throwing indexes at a schema without understanding the physical reality of the database, that just creates a fragmented mess. Putting the wrong column order on a composite index basically makes it useless. Ignoring index maintenance leads to massive bloat. Indexing low cardinality columns, like a simple Boolean status flag, wastes memory for zero gain. And the absolute worst offender of them all, leaving a transaction idle. This usually happens because someone foolishly put an external API network call inside a database transaction block. It locks up your database workers and completely grinds your entire application to a halt.
Let's shift gears to distributed system nightmares.
Zooming out from a single database, the training wheels really come off when you scale out to a distributed architecture. To grasp the sheer scale of the problem here, consider this. At hyperscale companies like Uber, a single ride-hailing request can trigger over 30,000 remote procedure calls across 500 different microservices. When your architecture is that deeply interconnected, you introduce a terrifying combinatorial explosion of failure modes. Just a tiny, seemingly harmless latency spike in a non-critical downstream service can cascade and take down your entire core business.
Because of this massive scale, even basic maintenance becomes incredibly dangerous. Imagine a 100 million row database migration that just times out halfway through. You can't roll forward and you can't roll back because the database is locked. You're left with a zombie schema. Senior engineers prevent this by enforcing strict guardrails, mandating zero downtime policies, ensuring every single migration script is idempotent so it can be safely retried, and strictly separating schema changes from massive background data backfills. You have to treat the database like a live organism that absolutely cannot be stopped for surgery.
Then, of course, there are the self-inflicted wounds. You add an in-memory cache, like Redis, thinking, hey, this will save my database from high traffic. But if a highly requested key expires and 1,000 concurrent requests suddenly miss the cache at the exact same millisecond, they all rush the database to recompute the value. If you don't manage your expirations properly or implement a debounce mechanism, you have just engineered a cache stampede, also known as a thundering herd. And yes, it will instantly take down your production database.
This nightmare easily extends to your infrastructure orchestration too. Let's say a stateful Kubernetes pod gets stuck. A junior dev might just forcefully delete it with a grace period of 0 just to clear their dashboard. But if the pod isn't physically dead, you've just corrupted your distributed state. A senior engineer never relies on humans making the right choice under pressure. They implement automated fencing to physically sever broken nodes, enforce strict storage topology limits, and use RBAC rules to explicitly deny developers the ability to run dangerous commands. They design systems where doing the wrong thing is physically impossible.
Next up, the architecture of trade-offs.
In the realities of scale, there are no perfect solutions, okay? Only calculated compromises. Notice how tweaking just a few configuration parameters completely shifts the balance of your entire system. Take Apache Kafka. If you increase linger.ms by just a few milliseconds, you slightly increase your latency, sure, but you drastically increase your throughput by allowing messages to batch. Or look at tiered storage. This is huge. Offloading cold streaming data to an object-based data lake doesn't just clear up space, it reduces your high-performance disk footprint and cuts infrastructure costs by a massive 70 to 80%. Every single architectural dial you turn costs you something else.
We see these trade-offs in DevOps too. A junior mindset says, hey, let's replicate our entire staging environment for every single pull request so developers can test in isolation. Sounds great until you have 50 PRs a day and replicating databases and services triples your cloud bill overnight. The senior mindset accepts the cost-complexity trade-off by building ephemeral environments. They use autoscalers to scale idle environments to 0, and they implement a strict 48-hour time-to-live limit to automatically destroy abandoned testing resources.
At the core of these distributed trade-offs is the Pacel-C theorem. Now, we all know about the CAP theorem, right? During a network partition, you got to choose between availability and consistency. But Pacel-C adds the brutal reality of day-to-day operations. It states that even when your network is perfectly healthy, you still have to choose between latency and consistency. You want ultra-low latency, you have to trade away strong, immediate consistency. There is absolutely no escaping the physics of the network.
Even monitoring your system comes with massive trade-offs. If you try to log absolutely everything and foolishly use high-variance data, like unique user IDs, as metric labels, you will trigger a cardinality explosion. Every unique label creates a new time series, and suddenly your observability database costs more to run than your actual application compute. No way. Seniors control this by using tail-based sampling, keeping 100% of error traces but only maybe 1% of successful ones, and enforcing strict tiered retention rules.
Finally, let's talk about designing for failure.
Ultimately, system architecture is a reflection of team culture. You'll hear the term CYAE quite a bit. Cover your ass engineering. Mature engineers absolutely refuse to practice this. Look, everyone cuts corners to ship features. That's just the reality of business. But senior engineers explicitly acknowledge those trade-offs and tech debt up front. They document it. They own it. They don't point fingers or hide behind abstraction layers when those corners inevitably cause a system to fail. They take accountability and they fix the systemic process.
Which brings us full circle to our primary philosophy today. The best code is the code that doesn't exist. Think about it. It has no latency, it requires 0 compute, it has absolutely no bugs, and it doesn't wake you up at 3 a.m. Remember, the absolute fastest way to accelerate feature delivery across your entire engineering organization is to ruthlessly remove the complex, unmaintained barriers standing in everyone's way.
So I want to leave you with this final thought to apply to your own work right now. Review your own architecture. Find the bloated processes, the features hidden behind dead flags, the optimizations for bottlenecks that never even materialized, and just start deleting, because your future self and your entire team will absolutely thank you for it. So what are you going to delete today?